Welcome, everyone. My name is Diana Sinton. I'm a project manager contributing to iGuide's activities, and we are super excited today to have a group with us from our summer school last year. This is one of the teams that was led by Dr. Wenju from University of Illinois Urbana-Champaign, who's also with us here today. So why don't we get started? Xiao, you can go ahead and start sharing your screen.
Okay, thank you, Diana. Let me quickly
And
share.
again, I don't have the full list of who's going to be presenting from Team 5. So please go ahead when you get started. If you could introduce yourselves too when you're doing your sharing.
Okay. Thank you for your introduction, Diana. This is Xiao, part of the Team 5 led by Dr. Zhou. And last summer, we conducted a research on flood depth prediction through geospatial data fusion and machine learning. So today, we will be walking you through this project. The flood is one of the serious disasters that has been negatively affecting people's life. The total flood disaster cost now exceeds about 2 trillion annually, including the indirect and ecosystem impacts. Urban flood extent is growing annually by 5 to 6% in countries like the US, China, and India. By predicting and mapping floods, it can help improve public awareness and safety, protect human lives and property, enhance emergency response, and reduce economic losses. Development of flooding prediction methods can be divided into three stages. Before 2015, researchers mainly used physical process-based methods. Later on, between 2015 and 2020, traditional machine learning methods such as random forest, support vector machines have been applied a lot for flooding prediction. And after the year of 2020, as shown in the left figure, deep learning methods have been widely explored for flooding prediction. Let's analyze the performance of these three types of methods. In this figure, the first five rows are widely used physical process-based model, while the last three rows are typical machine learning methods used for flooding prediction. Compared to physical process-based model, machine learning model methods has higher adaptability and can quickly respond to the input data. Compared to traditional machine learning methods, deep learning enables end-to-end learning by automatically feature extraction from complex data structures. Thus, it has been widely used for flooding prediction in recent years. However, the performance of deep learning is highly reliant on data quality. In particular, the quality of label data directly influences the model generalization ability and its effectiveness. In the real-world applications, according to the statistics, 50% of research use computer simulation data results, namely the output of physical process-based models as label data, and around 33% used field measurements data as label data, while the last 17 use online data as reference data. The online data involves the images and text from social media, news, and some apps like a Crowdwater, but it is usually with unstable data quality. So from the year of 2022, the usage of the label data is decreasing while using computer simulation data has obviously increased. As shown by the importance and methods above, the question that are driven behind is how can we generate a high quality data set supporting machine learning networks to predict flood depths for both rural and urban areas, and how we can develop a model using manual target measurements to rapidly predict flood depth before an event. Previously, the simulation data is different from the reality data, so it will lead to error propagation when used to train the deep learning model. And this type of data also have a relatively low spatial low spatial resolution. Sensors, gauges, and observed water depth records are representative types of field measure level data. However, sensor and gauge-based measurements face several limitations, such as sparse spatial coverage, high installation charges, and um, data quality issues. But compared to data from the sensor engaged, the observed water depth records are usually more accurate. Besides this data, some studies has also used Sentinel-1 as label data to identify flood or non-flood area. Sentinel-1 images cannot provide height and usually with long visit time, but it can provide the real data and can cover wide areas. Our project has provided both the Sentinel-1 images and observed water depth data. The picture shows the conceptual hydrological method and reflects the main factors that influenced flooding. From the top to the bottom, our project provided the historical precipitation data downloaded from open media and also the DEM data from USGS and soil moisture active passive satellite images, as well as the Landsat 8 from Google Earth NG. In our dataset, we use flood depth as our target features. This is ground truth data from high water mark data of USGS, manually collected samples from flood events, and more than 1,000 records have been spatially and temporally aligned with Sentinel-1 SAR images. Our dataset is the first high watermark SAR aligned flood depth dataset, combining 1,219 USGS high watermark records with Sentinel-1 SAR images. And we use a multimodal feature integration pipeline by integrating SAR, chirps, rainfall meteorology, DM, soil moisture, active passive data, and Landsat features. This is high quality real world depth labels overcoming limitations of crowdsourced, simulated, or sparse gauge data. We explore feature response relationships among these input data and flood depth using random forest model, which serves as an interpretable baseline. Then I will pass the detailed introduction of the data set to my teammates, Tammy.
Yeah, thank you. So just as mentioned, that multimodality data were used for our research. And here, in this slide, I'll be explaining some of the features that was used and as well as the data set that was used. So we made use of the synthetic aperture radar, where we actually get our polarization features, including the VV and the VH, in which we summarized using 1.5 kilometer by 1.5 kilometer spatial window. So the summarization led to some features, including the minimum, the maximum, the interquartile range, as well as the standard deviation. And this particular data set was sourced from Sentinel-1 using the Google Earth engine. And other data sets we use include the precipitation data, which was sourced from CHEPS and it provides the high resolution rainfall estimates. And at the same time, we use some meteorological data sets where we got the temperature, the humidity, the wind speed, where we sourced from our Open Meteo API. And at the same time, we use the digital elevation model, which provide the slope and the elevation information, which was sourced from the USGS 3D elevation program. And to get the land cover features, such as the impervious surface and vegetation and some other land cover features, we made use of the NLCD land cover dataset, which was sourced from the NLCD provided by the USGS. Yeah, next slide, please. And then after we made we extracted these features. So here on this slide, we have the Jupyter Notebook, which is currently on the HiGuide platform, which shows the steps we took in pre-processing and at the same time combining our data sets together. Since these data sets are coming from different sources, we actually pre-process them and we combine them to have a single data frame, which will be used as inputs in our model, which is the random forest that we'll be talking about in the next slide. Next slide, please. So here it summarized the it's an image showing the combined features. So from our combination, we have 53 features all together merged, which will serve as the input into our model that will be trained, which all these are also present in the HiGuide platform for reference purpose. Next slide, please. Yeah, so the baseline model that will be used is the random forest. Like I mentioned, we have 53 features, which include different basic identifiers, impervious surface metrics, land cover proportions, elevation statistics, at the same time has the polarization statistics that I mentioned. All these features combined made up to 53 features. And for the output, which my colleague have mentioned, made use of the flood depth. Yeah, so I will pass it over again to Chen to talk more about that opinion. Yeah.
Hello, everybody. I'm Parnian Ghaneei, and thanks to my group mates to go over the introduction, explaining the research questions that we tried to answer, as well as data pre-processing. So I'm going to share my screen. So for the first experiment, we wanted to select a model which is simple and also it gives us a good performance. That's why we selected random forest, which is an ensemble-based model that randomly subset data into different decision trees. And at the end, it averaged them all to get a combination of ensemble members and the final results. And so, as my group mates mentioned, we had 53 features and predictors, and the flood depth was our target variable. Now I'm switching to the notebook that is available in the iGuide platform. Sorry. Can you see my screen, guys, still?
No,
No.
not yet.
Not yet.
Okay. Still not?
Nope, not yet. There we go.
Okay.
Yeah,
Yes.
we have it
Okay.
now.
So this is our notebook for the random forest model. That first we have a short summary of the data set and predictors that we used. And we import the required libraries and we go to the data preparation. So we combined the predictors and the features into a single CSV file that we can easily read them. And we define the target variable as well as the predictors. We split the data into 3 parts: training, validation, and test, with 70% for the training, 15% for validation, and the same for the test. We normalize the data sets, and we train the random forest model. And we also have some different boundaries for hyperparameters. We run a random search to get the optimum values for each hyperparameter. And after finding them, we do model evaluation. We have different metrics such as mean squared error, root mean squared error, and mean absolute error, and as well as R squared. And we have some plots about the results. For example, here the scatter plot shows the performance of the model for training, validation, and test, as well as residual plots. And for the small amount of data that we had, the model was doing good. The performance was good. And also in the next step, we were interested in looking into the contribution of each feature and how important are they and their effects on the model accuracy. We categorized the feature importance into different categories. For example, land cover, weather, and sentinel were the first 3 most important features for the results of the random forest model. And here we have some plots about the feature importance. And also we provide model summary and some other details, which are all available in the notebook and is uploaded into the iGuide platform. Now I'm going back to the slides to show some special maps of the results that we had. And so here you can see the absolute residuals in meter for the data set that we had, and also based on the histogram, the performance is good with the random forest model. And also in the next step, we were interested in comparing the underlying pattern that the random forest model could capture against the target variable. So we used unsupervised machine learning clustering method to group the depth values into different groups and see how the model could follow the target variable, the real patterns of the data in the target variable. And as you can see here, the model is doing a quite good job in finding the underlying pattern, and it follows the patterns in the target variable that we had. And here I'm showing 2 examples of the performance of the model to close data points in a urban area. And as you can see, in both of these data points, the model is capturing the value and it's predicting the value with a good performance. And now I'm passing the presentation to one of my group mates to go over another experiment that we had with feature routing method.
All right, thank you, Parnia. Why don't you let me share the screen so that I can control it easily?
Sure.
Can everyone see my screen?
Yes.
All right. Thank you, Parnia, for the introduction. And yes, so I think it's very visible to everyone. The results of random forest model is actually quite exciting. In general, as you can see, the absolute differences between the predicted value and the real manually collected high watermarks is like within 2.2 meters. So I would say this is pretty good results already. Uh, but because our baseline model they are from a multimodal sources. For example, we have satellite images, we have manually collected point data, soil moisture, temperature, all that kind of things, time series. That is what inspired us to use the technique of feature routing based deep learning. And this particular technique has been published in another paper that the first author being me. It has received 2 awards, International Cartographic Association Scholarship and Cargis Grant. And the citation is right down there if you're interested. But again, the whole idea under this feature routing method is that we want to align data sources into their respective best processing way. So for example, if we have temporal data, we should probably put in a temporal fitted processing pipeline. If we have imagery data, we should probably put it into a convolution. If we have a point data, we should probably put it into a multi-layer perceptron. So that's exactly what we did in our second experiment, putting feature routing method into our dataset. So we group our extracted features into different groups based on their traits. And then we feed them into 3 distinct pipelines, being LSTM and convolution and modulated perceptron. And we fuse their results through a dedicated fusion layer using multi-head attention, which is quite conventional in these days. And then we take the largest output from the fusion layer and eventually compile it into a prediction as our results. So this is the high level idea. And how we really implement it is really just going through a permutation of directing each features into different routes, route 1, route 2, route 3. We can direct this feature into different routing. And we have these different combinations and of course, the results are really, really exponential numbers of combinations. So that's why we end up with a randomized grid search for the optimal routing. And this is each route is evaluated by MSE. And the final results we have is an MSE of 0.254, which is pretty close to what we have using a random forest in terms of, because this is square error, if we translate back to the average absolute differences, it could be up around 0.5. So we also have a visualization similar to what we have for the random forest results. And these are the 2 same data points in the urban setting where we have 2 very close data points. And as you can observe, the prediction for the data point that's far from the road, we have the predicted being 1.08 meter, and the real one is 1.05. So that's very, very close. And the one far from the road is closer to us. It's about zero point 0.3 meters differences, but it's still quite, I don't know, acceptable given that we are really talking about flooding events that's potentially adaptable in real life scenarios. So this is urban setting. And right, so this basically are our work on the feature routing modeling part. And Dr. Zhou, do you want to do the conclusion or?
You can continue.
Okay. Sure. So to conclude our project, so some of the things we have done includes first we built the first large-scale high water marks and SAR aligned flood depth dataset. So I want to just quickly explain that why we have only about 1,200 data points. This is because the SAR data, they have very long retrieval intervals. And if we want to really align those data with our high watermarks, which also have timestamps, it becomes a little problematic. So it eventually actually filters out a lot of our data points. So that's one of the direction of our future work. And but still, this is the first large-scale using the manually collected high water marks SAR aligned flood depth dataset. And then we developed a multimodal flood depth estimation framework combining SAR, precipitation, meteorology, DEM, soil moisture, and Landsat. And we do provide a foundation for near real-time and pre-event flood depth estimation for disaster response in the future. And then we also provide a scalable baseline for pre-event flood depth estimation based on our random forest and feature routing methods. So future work, I'll just continue. As I said, enlarging the dataset by leveraging additional SAR data, such as Umbra, will significantly enlarge our base dataset because of the scarcity that we mentioned, so that we have better alignment. And then we definitely want to explore more urban versus rural flood height classification because the current dataset relies heavily on urban data points. And making that distinction would be interesting. And then we also want to expand beyond just extreme flood events because currently we are focusing only extreme flood events. Beyond just these events will help us to get a precaution alarm system. And then eventually you want to involve new input data such as satellite embedding of Alpha Earth's foundation that would be very beneficial for machine learning purposes. And yes, thank you. This concludes our presentation, and we welcome any questions from the audience or comments.
Thanks very much, Team 5. I'm excited to see the work summarized like this. Are there questions from the audience? Feel free to type them into the chat. And you're also welcome to, if you trust your microphone and your background audio, to ask the question live. And while the group thinks of what questions they might have, I'll kick off the discussion with a question. I remember at the very beginning learning about the use of the high watermark data, and I'm wondering from the team, was it how many of you were surprised that that data set was as relatively small as it is, and that it hadn't been used as much as it could have been before? I'm just interested in your thoughts on the use of that data set, the high watermarks. And that's a question for anyone on the team.
Anyone want to go ahead?
So I think at first we had about, I'm not sure, correct me guys if I'm like wrong. So we had about 6,000 or maybe more data that when we matched them with the Sentinel, then we came up with 1,200 data points. And it was really surprising for us because at first we were thinking about starting with maybe convolutional neural network and some deep learning methods. Then we came up with a very small data set. And yeah, that was the reason that we first start our experiment with the random forest.
Mm-hmm.
And so, yeah, maybe for the future, including other data would help us.
It seems like high watermarks is one of those that physical evidence that just hasn't been leveraged enough in the same ways, enough adequately in the past to be able to continue to use it in additional ways.
Yeah, exactly.
Yeah.
Yes, I can add a little much more information about that. In fact, the high watermark data, they only provided the water depth, the flood depth and flood elevation, but have not give a relative accurate timestamp. So what we have used this data is we have used the surrounding gauges flood peak time to align to that high watermark data. And this alignment process also filtered a lot of high water mark data because not all these types of data can find the aligned gauge data. So I would say that's a new way to use this high watermark data. We have assigned a relative accurate time step to it. Then it can help us to acquire, especially the time series data, because what we do is a flood forecast. We have a forecasting the flooding 1 hours before the flooding peaks, 1 hours before it happened. Yeah, so the time step is really important for us.
Right.
Yeah.
Yeah, that makes sense. So thanks, Jikun, for posting the link to an article related to this. It's there in the chat. And we have another question from Glenn. I'm going to paraphrase or read this question here for the group, unless you'd like to come on live. He's wondering whether you've considered using flood modeling data, the HEC-RAS results, into the training data since high water marks are limited. The Illinois ISWS, might be the Illinois State Water Service, has conducted extensive modeling over the state of Illinois for FEMA mapping. So is the group when have you wondered about the HEC-RAS data?
Yeah, I think that's really a very good idea, an exciting idea that we can combine both the simulations data and the real world observation data together to see what will happen. But yeah, we haven't done this experiment, but that's very interesting direction. We will do that.
This is Glenn. I'm the guy who posted the question. Just to add on to that a bit, the models that we have are publicly available, and they do cover most of the state of Illinois for extreme events, the 1% annual chance flood, in terms of floodplain mapping for the Federal Emergency Management Agency, that we've performed that work for the last 20 years. So we have an extensive archive of models that have been validated against national standards for floodplain mapping. So it's quite a resource that you might want to consider talking to us about and seeing if we could collaborate somehow.
Thank you. Yes, that's really a good suggestion. And currently, if we go upper to the dataset distribution slide. Yeah, we can see that we haven't. It seems we haven't. Yeah, already passed the map. Yeah, this one. Yeah, the map. No.
No, probably
The
not
US map. The US map one. Yeah, this
There we
one.
go.
Yeah, we can see that we haven't contained the samples of Illinois, and also many we mostly they are located at the those states and cities near to the ocean areas. So that's really a good idea, and it can provide the flooding information for those inner cities, inner land areas.
I'll just quickly add the point that that's very great idea. But so one of the key motivation was using manually collected data set so that we are actually reflecting on some of so it's not just from physical modeled data set. But I think integration of physical modeling is inevitable if you want to scale up. So maybe we can apply some certain kind of weighting to manually collected or physically derived data so that it still captures our main motivation in some perspective.
Yeah. Actually,
Yeah,
it's a
also, yeah, go on.
Go ahead.
Yeah, so I also agree with what Jikun just mentioned. I know some studies that have actually worked on prediction of flood, and one of the challenges that they've encountered is seeing ground truth, right, which is measured manually, which we used here, right? And I know that some studies have also combined manual data sets at the same time with modeled datasets to actually serve as targets to actually to compensate for the scarcity of manual observations. So I strongly believe that it holds great opportunity combining that also, in as much the data set is actually maybe in a way has been modeled and it should perform well, I believe so. So combining it, yeah, I think it holds great opportunity for what we're doing here. Thank you.
Or maybe we can like use the outputs of the physical model conditioning some observations that we have about water depths to the model, to the estimations from the model, improve the model outputs, and then using them as targets. We can use some kind of Bayesian conditioning tools to combine them, merge them, and then use them as a target variable. Yeah, that would be great.
Sounds like the group has some ideas for some things to work on next.
Yeah, sure.
We have S. Shekhar, which I'm guessing might be Dr. Shashi Shekhar. Hi, Shashi. Wondering what is the flood depth estimation is quite impressive. What's your secret sauce here? For example, what's the horizontal and vertical resolution of the elevation map? And does it include any building geometry details? And Shashi, I'm glad you were able to just yeah, you're welcome to add more to that if you want to unmute yourself. And thanks for turning on your camera.
No, it's accurate. I just trying to learn because yeah, the accuracy was almost in centimeters, so very impressive. Thank you.
Tammy, do you have anything for discussion?
Yeah, that's a great question. Yeah, about the resolution of the elevation map, I'm not sure about that. I'm not sure if Dr. I don't know if you have any information about that. But one thing I know is that when we were preprocessing the data sets, right, like we mentioned, for example, for the SAR dataset we used, I think we made some initial experiments, right, in choosing the spatial window that we use. We consider the fact that if we use so much spatial window, that might affect our prediction. So one thing we take into consideration is right from the preprocessing of data sets in such a way that we consider a lot of things. I remember we had a lot of discussion trying to make sure that we actually did this pre-processing very well, because I believe that the result of our prediction also depends on the quality of our data set, right? So I may not be able to provide the exact, resolution of the elevation map that was being used, but I just, love to mention what we put into consideration while pre-processing our data sets, right?
Right.
So
Oh, sorry.
I think, go ahead.
Oh,
Go ahead.
Yeah,
okay.
in fact, what we have predicted is only the point levels data rather than a map.
And also
Yeah,
the
so,
elevation was in 10 meters. The USGS 10 meter DEM, we used that one. And also we provided some statistical. So at first we wanted to go with a deep learning model that can consider the spatial dependencies of the data, like images that we had. So, but we were limited by our target variable. So we informed the model with some statistical information of the images that we had. So the model has seen some statistical about the images, but it's trained on the points with the 10 meter resolution DEM.
I can also share the screen to where we got the data source. I think, please correct me if I'm wrong. So I think we got like as Parnian say, we got the data from the USGS, and it has multiple data source about the gauge, the water height, and the highest water marked. So it has the elevation, it has in feet matrix, and when we do a conversion from feet to meter in our projects, and that's how it could be like.
I Yeah, a little bit correct. Here we can see that for this sample, what we have used is the height above ground attributes, but here these samples do not have. But what we have used is selected those high watermark data with the height. Yeah, so that's also the one reason that why we have so very limited samples to use, and why we haven't used the elevations here is we found there's some uncertainty. I think I would trust the flood elevation here more because it is manually uh, uh, measured by human by this point is specific to this point. But for the three depths, it's generated using the LiDAR, right? So in some area, there's some uncertainty problem of that area, that point's elevation. So there's a phenomenon that for some points, if we use the flood elevation to measure the ground truth, the ground elevation, the value is negative. Yeah, so we cannot use this way to generate the flood height. What we can do is to just use the height above ground value generated by the USGS.
Okay. So may I ask a follow-up question here?
Yeah.
Yeah. So usually the machine learning methods are better at interpolation than extrapolation, right? So if you actually had the flood level information about some nearby points, and then you're kind of using neural network kind of to simulate kriging, it's likely to do better. However, if there is a completely new flood, right, where you don't have the data from any point yet, and you wanted to use your method to guess the flood depth. I mean, have you tried that? I mean, do you see any difference in performance in interpolation versus extrapolation?
We currently we haven't do the interpolations work. Yeah, we firstly we need to make sure for those point data we can regress it relatively accurately, and if the accuracy is good enough, then we can do an interpretation. Yes, to generate a 3D map, 3D flood map. Yeah, but yes, that's an exciting word, but that's also depend on there's many indicators will influence that, especially the land cover will change. We cannot only use the DM, right? Because according to Parnian's sharing, we can see for the feature importance of those input data, the land cover and the land use also plays a very important role in this process.
All right. Thank you so much. Yeah, thank you.
Yeah.
And also, I would like to add that the test dataset that we used for testing our model was completely out of sample. So those flood-like events that we tested the random forest model with wasn't like used as an input to the model. They were completely out of sample for the random forest model.
I think one major obstacle that prevents us doing the spatial interpolation, like you mentioned, kriging, is because of how scattered our dataset was and how scarce really our dataset was. Because from those dataset, we cannot really infer reliable spatial relationship to perform those interpolation or exploration. So I think that's a very interesting frontier. If we decide to move on with the combination, the augmentation using physical modeled results, that could be a pretty exciting direction. And I just going back to your very, very first question, being what is making our flood depth estimation being really good in general in terms of results. I think one of the key reasons is our data set was very, very varied, and we have a lot of statistical analysis results of those features being directly feed into our model. For example, for the Sentinel satellite imagery, we actually do a point-based summary of neighboring information. For example, how was the difference, like the interquartile range of our elevation differences. We feed those into our model, and we also use random forest and a feature routing that apply the different processing that basically enabled better representation of our processed data set, so that I think it's a combined effort. I would just say. So yeah, I think the results are pretty good, so we're happy about it. But we can take a step further to all this direction you mentioned.
Cool. Thank you so much.
Before I turn to the question about precipitation data, I just wanted to make the observation that this is the kind of work that we like to do at our summer schools, where we bring together scholars from multiple different backgrounds. And we've got geographers, geoscience people, hydrologists, statisticians, some people with expertise in AI and modeling in this case, and have them work together on an multidisciplinary project for the week. So this is an example of convergent science at its best. We're really proud of the work that our teams do at the summer schools. And we've got a question here from Sanjay about you all had used CHIRPS data. How anyone have any thoughts on how CHIRPS differs from NOAA's Atlas 14 data, which is often used for stormwater and flood related design work?
Yes, I
Okay.
can answer this question. To be honest, we have used the CHIRPS data, and we also involved a much more accurate rainfall data in our downloaded the meteorological data from the OpenMetria API. So that can provide us a much more fine temporal resolutions rainfall data. And here, why we haven't considered the NOAA Atlas 14, because that is a rainfall frequency statistic data. It's not a real-time weather forecast data. But what we have do is we want to train a model. Once we get the current rainfall situation, we can predict the 1 hour later flood situation. We want to do these types of early warming research. So that's one of the reasons.
It sounds like it's reflecting the trade-offs, decisions you have to make about temporal availability and utility for different modeling purposes. Any other questions from the audience? Or any follow-up from any of the team members? It sounds like you've continued to do some work together since we were there in August and have more ideas for future work. That's exciting too.
Yeah, this is a very valuable opportunity. I really learn a lot. And
Yeah.
Thanks to our team leads, our teammates, I really learn a lot from them as well.
Yeah, this is a group they don't know each other until first thing Monday morning. And then they've got basically 4 days to figure out a project and work on something together. So it's
Yeah, I'm so
Yeah.
enjoy working with all of my teammates. They are so talented, and when we come together, we have get up some new idea. To be honest, that's also one of my ongoing work. So many things I'm also not so. I mean, I don't know much too, right? But my team is giving me much more idea to this work too. And I also very excited to see how it performs, looks like. yeah, before that, I also do an experiment. I know, okay, this is a possible way, but we haven't tested other methods. But when we work together, we comes to other methods. It's so exciting. I very enjoyable for the summer school.
Thanks for describing that. And that's perfect, perfect intro to this last comment we have here in the chat, a current student from University of Connecticut from UConn, asking about next year's summer school. We are going to be having, iGuide will be having another summer school in summer 2026, just some number of months away. The plan is to have it in July. There is a very, very good chance that it will actually take place at University of Illinois Urbana-Champaign, rather than the University of Minneapolis, where it's currently being advertised for. But we will also have that website and the application process being posted. It'll be updated probably next week with final information. We're about to put out a call for team leaders. So the same way that that when asked about leading a team for last summer, we will be soliciting projects to work on for summer 2026. And then a little bit later is when we open up the application process for students to participate. So if you are whether you are a student interested in being part of our upcoming summer school, or whether you are a researcher that has a project that might be suitable for this, pay attention to the iGuide Summer School webpage, which I will really quickly put into the, how quickly can I get this? Very quickly. Here is the webpage. It does still say University of Minnesota Twin Cities, but again, very likely to be migrated to University of Illinois Urbana-Champaign. And while we're at that, so pay attention to that website, because all the calls will go there. And then just to remind everyone, this group highlighted the data, the notebook that it has on the iGuide platform. And that is also a very important open resource. I've also just put the link for the platform. And a very important resource that we want to make available to the community as a whole, where these notebooks can reside, these Jupyter notebooks, where you'd be able to access some of the iGuide provided computing capacity to even execute notebooks right there. So pay attention to our platform site. We're adding new content all the time. We call the content knowledge elements. That can include Jupyter notebooks, data sets, models, educational resources, publications. All these things can be linked elements within the platform. And Anand has helpfully reminded us that there's a contact us page there that has where you can sign up to be part of the iGuide group. You can get announcements for the summer school, specifically when calls go out. If you go there and sign up for the emails, it'll come just about the summer school. So we're almost at the top of the hour. Thanks very, very much to Team 5, Summer School's Team 5 from last year, for sharing their work. If you look at the VCO webpage, you will find recordings of other teams that have made their presentations. Any final question? In the absence of any final questions from the audience, I want to thank again Wen and the team, the students that worked with her. And we will sign off. Again, this recording will be processed and then it'll be up on the VCO website for other people to refer to. So thank you all. We have the next, take a look at those VCOs. We have the next several weeks filled with other flooding related topics too. We're kind of on a flow with flooding, no pun intended. So check out the VCOs, and iGuide will be in touch soon. Thanks, everybody. And Anand, thank you for just putting the VCO link right there.
Thank you very much.
Thank
Thank
you.
you.
Thank you, everyone.
Thank you.
Bye-bye, everyone.
Bye.
Bye.